Hello everyone, this is Tianyang Jiang from Tsinghua University, and I'm happy to introduce Aurogon, a distributed in-memory transaction system that tames aborts in all processing phases. The use of online transaction processing, or OLTP, has been increasing, especially in web service and e-commerce. Many operations of infrastructure can also be implemented by transactions, like rename operations in a file system. OLTP applications have two features. First, it shows severe skew in data access frequency. We call it data hotspots. Second, requests in OLTP often have data dependency, like read-modify-write operations. The growing demands of OLTP applications promote distributed transaction processing from rack scale to data center scale clusters. The goal of transaction systems is to pursue high throughput and low latency. However, when multiple read-modify-write operations access data hotspots, transaction aborts will happen and impair the goal. Among existing concurrency control protocols, time-step ordering, or TO, is efficient in processing distributed transactions. It has two benefits. First, TO performs better than two-phase locking and optimistic concurrency control under high-contention workloads. Second, TO is easy to implement multi-version mechanism and support read-only transactions. In TO protocols, the time-step order is taken as the serial order of all transactions. And when requests are not executed in the order of their time steps, aborts will happen. We call this phenomenon request reordering. Let's take an example. In TO protocols, each transaction has a globally unique time step, and all requests it issues are tagged with this time step. Here we have two transactions, and each issues two requests. However, the execution order of requests does not match the time step order at key B, and one of the two transactions has to be aborted. So, in which processing phase will request reordering occur? There are four phases for transaction processing in TO protocols. First, the coordinator obtains a time step from clocks for the transaction. Second, the coordinator transfers the transaction's requests to the participants. Third, participants execute the requests, reading or writing local data, and return results to the coordinator. Finally, the coordinator determines whether the transaction can be committed. Request reordering can occur in each of the first three phases. Existing TO systems can be categorized into clock-driven approach and date-driven approach. The limitation of clock-driven approach is that they pursue the scalability of time-step allocators but relax the accuracy when they optimize time-step allocation phase. On the other hand, data-driven approach seeks opportunities to save transactions in the commit phase, but aborts are often inevitable at that time. So, we need an all-phase reordering-resistant distributed transaction system. Our key idea is to maintain the time-step order for requests in all phases. Here we introduce the reasons for request reordering in each phase. In time-step allocation phase, the issue is inaccurate distributed clocks. On the left, we show an example. Two transactions, transaction 0 and transaction 1, access the same record X. However, the order of time steps that two transactions obtain is not consistent with the physical time order. Transaction 1 obtains the time step before transaction 0, but gets a larger time step, 4 in blue box. It makes transaction 0's write fail, because in TO protocols, requests that conflict with each other should be executed in the time step order. We evaluated the impact of inaccurate distributed clocks. A 10 millisecond error of distributed clocks leads to a 94% throughput decrease of TO system. In request transfer phase, non-uniform data access latency results in request reordering. The latency of accessing local data in memory is 100 nanoseconds, while the latency of accessing remote data via data center network is 2 microseconds. The gap leads to request reordering. Let's take the same example, but this time we have accurate clocks. Note that transaction 1 and X are on the same server. Although transaction 1 gets a timestamp after transaction 0 this time, it reads X earlier due to local access. As a result, transaction 0's write fails again. In request execution phase, dependent requests lead to request reordering. Dependent requests depend on the previous request's results in the same transaction. In this example, transaction 0's request is to self-increase X with 5. So read X of transaction 0 must wait for the result of read X. Read X is such a dependent request. However, transaction 1's request is executed between transaction 0's two requests, and it results in the failure of transaction 0's write. The core reason is that dependent requests will be issued late due to dependency wait. In order to maintain a timestamp order for requests in all phases, we need to solve the above issues. Here we have 3 challenges. First, both background clock synchronization and foreground transaction processing require CPU resources. How to achieve high accuracy for distributed clocks under severe CPU interference from transaction processing? Second, scheduling requests is necessary for maintaining a timestamp order, but scheduling could make some requests take longer time to finish. How to design a scheduling strategy with moderate latency rise? Third, all requests within a transaction must see a consistent snapshot and modify data consistently. How to execute these dependent requests consistently and efficiently? We propose Aurogon, an all-phase reordering resistant distributed in-memory transaction system with solutions targeting the 3 issues. In the timestamp allocation phase, to achieve high accuracy for distributed clocks, we adopt a 2-layer clock synchronization mechanism called 2L clock. In the request transfer phase, to mitigate the impact of non-uniform data access latency, Aurogon defers requests adaptively when participants process requests. In the request execution phase, to prevent dependent requests from being issued late, Aurogon pre-attaches the metadata of dependent requests to target data before execution. We give more details about these major solutions in the next few slides. The accuracy of clock synchronization will be influenced by foreground CPU interference. Specifically, the latency of a synchronization probe will fluctuate due to interference, which impairs the accuracy. A probe synchronizing 2 clocks includes 3 operations: timestamping at clock A, issuing a query for the time of clock B, and timestamping at clock A again. We have an observation that probes synchronizing CPU clocks with NIC clocks experience a larger latency fluctuation than probes between multiple NIC clocks in transaction systems. The figure on the right shows that the ratio between P3 nice and median latency of probes in CPU NIC synchronization reaches 6.8. To this end, 2L clock separates the synchronization process into CPU NIC synchronization and NIC-NIC synchronization to adopt different methods respectively. The synchronization process is shown below. First, each CPU clock synchronizes with its local NIC clock. Then, all NIC clocks in the cluster synchronize with a reference NIC clock. The NIC-NIC synchronization links are organized as a tree. For CPU NIC synchronization, 2L clock discards out-layer probes according to probe latency. It helps to achieve high accuracy. For NIC-NIC synchronization, 2L clock uses RDMA, an emerging network technology, to reduce CPU usage of synchronization. Here, NIC A needs to synchronize with NIC B. First, it sends requests from NIC A to NIC B with a combination of RDMA UD mode and RC mode. The optimization prevents the involvement of server bits CPU in the critical path of synchronization. Second, 2L clock transfers the timestamps generated by NIC B asynchronously to server A in batches, so server A can calculate the clock offset between NIC A and NIC B with these timestamps. Aurogon defers read requests to tolerate late arrivals of write requests. Let's take an example. Transaction 1 and X are on the same server, so transaction 1's request arrives at X earlier. After receiving transaction 1's read, the participant of X defers it for a preset interval instead of executing the read immediately. Then, transaction 0's write arrives and can be executed successfully. Finally, transaction 1's read succeeds too. To alleviate the rise of transaction latency caused by deferrals, Aurogon uses two methods. First, we find that requests executed on data hotspots have a higher failure rate, so Aurogon only defers requests on data hotspots to cut the deferred read count. Second, Aurogon shortens the request deferral time heuristically to avoid presetting an overlong deferral time. Now, for dependent requests. In existing TO systems, a read-modify write operation requires three network communications: a read, a write, and a commit. It leaves a vulnerable interval from read's finish to write's execution. Other requests which arrive during the vulnerable interval could make the write fail. To avoid this, Aurogon piggybacks the write's existence with the read to target data in the first communication. Before reading X, the participant will first install a version into the data list, leaving the version's value as null. In the second communication, the participant will fill in the value of this new version. Thanks to the method, Aurogon not only eliminates the vulnerable interval in read-modify-write operations, but also saves one network communication and cuts unnecessary network traffic. Our evaluation is done using a 5-node RDMA cluster with server configuration listed here. We tested with both TPC-C and YCSB benchmarks. For comparison, we also test the three state-of-the-art transaction systems: a clock-driven approach DST, a data-driven approach Sundial, and an RDMA-enabled system DRTM+H. We adopt two common configurations for TPC-C and evaluate the systems under high contention TPC-C and medium contention TPC-C. We vary the local rate from 0 to 99% to adjust the ratio of records that transactions access in remote servers. When the local rate is low, adaptive deferral in Aurogon can reduce aborts caused by non-uniform latency of increasing network accesses. Aurogon outperforms peer systems by up to 4.1 times in throughput and cuts average latency by up to 86%. Now to YCSB benchmarks. In YCSB, each transaction issues 8 requests. Requests are either reads or read-modify writes. We test two YCSB workloads, all read-modify writes and 50% read-modify writes. Aurogon outperforms DST by up to 4.5 times in throughput and cuts the abort rate by up to 60%. Under 50% read-modify writes workloads, Aurogon achieves a larger performance improvement. It is because more reads will interrupt read-modify writes execution more frequently, and Aurogon's pre-attaching method works more efficiently here. Then we list some other evaluations. A zooming evaluation shows that all three techniques reduce the abort rate significantly. We also compare 2L clock with other clock synchronization methods. 2L clock reduces the average synchronization errors by 51% and P99 errors by 2.3 times compared to an existing solution Huygens. Meanwhile, we also replace 2L clock with other clocks in Aurogon to verify 2L clock's advantages. As a result, 2L clock brings an up to 31% throughput increase compared to other clocks. To summarize, Aurogon alleviates request reordering in all phases of distributed transaction processing and reduces aborts. The source code of Aurogon is available at this link. Thank you, and we're happy to take your questions.